All right. This week we're going to be talking about deltas and coasts. So we'll start off, this will be broken up into two different lectures. The first of these two will focus on deltas. So deltas form by the accumulation of sediment that occurs when a river discharges into a standing body of water, right? So as you have a river that's draining a continental environment, as that river reaches the coast, either of the ocean or of a lake setting, there are a number of processes that occur to create the delta morphology that we are going to talk about in this class. So there, as you can imagine, multiple processes, including the slowdown of the river component that occurs because you create a backwater. We'll talk a little bit about backwaters, which can cause sediment to fall out of suspension, of course. There are wave processes and tidal processes, longshore currents, and so forth that can all serve to modify and change the distribution and deposition of sediment on a delta. Deltas are called this because Herodotus in around about 400 BC, at least according to writings, thought that the alluvial plain of the mouth of the Nile River looked like the letter delta. Therefore, these are deltas. So this is the Nile River Delta, for example, here. You can see that it's kind of triangular in shape here. This is a really interesting delta. You can see one of the main features of the Nile River Delta is the fact that it is the location where water exists and is therefore also the location where agriculture exists. It also floods regularly, inundating the floodplain, bringing fine sediment onto the floodplain, allowing agriculture to take place because of the presence of nutrients that get delivered by that fine sediment. Deltas, as sort of natural areas of sediment accumulation, have built out huge amounts of land surface over the last 7,000 or so years. There's about 10,000 or so square kilometers globally of new land that has accumulated since sort of the middle Holocene. And here's some great examples of some of these deltaic environments, some of which are actively now losing land, like our delta home here. So this is, of course, the Mississippi River Delta. This is the Ganges-Brahmaputra Delta. This one is the Yangtze River, and this is the Nile River here. And so you can see that as these deltas build out, new land is created by the sediment that's being deposited into these systems. We care a lot about deltas for many reasons, the main being that deltas globally are home to enormous amounts of population. Over 300 million people worldwide live on a delta. They're home to some of the world's largest mega cities, including Shanghai and Calcutta, Cairo, Alexandria, so forth. Here we are in New Orleans, and we're certainly not a mega city compared to these. But they're also vital resources in terms of agriculture, fisheries, and other ecological resources. They're huge habitat for migratory birds and all those sorts of things, dolphins, etc., because they exist oftentimes in a fairly unique salinity gradient and all sorts of other processes that go on to make them really important ecological resources. they can also be huge shipping and commerce arteries. Like obviously anyone who lives here in New Orleans who's been out to the river has seen the amount of shipping traffic that travels up and down the Mississippi River. One kind of neat thing that I did this on the I was standing out, I think, at the Fly maybe when I first moved here, and I was just curious, thinking about the shipping traffic on the river, and I looked up on my phone that we now ship more cargo tonnage on the Mississippi River than the Mississippi River transports sediment. They're very close in order of magnitude, but at least the estimates, they're probably within any error if you were to do a proper error estimate, but they're about the same, if not shipping is a little bit more than the sediment load of the Mississippi River, which I thought was a really interesting notion. So more shipping than sand and mud gets moved down that river, which is pretty cool. The distribution of river deltas is not necessarily uniform across the globe, and it depends on a variety of things. Not every river meets the sea and makes a delta, but every delta occurs where, you know, a river meets the sea, right? So here's a neat map of the number of rivers, right, that reach the coast this is from a large global river delta database that was just compiled a couple years ago, and you can see that it's not a uniform distribution either, but it's a pretty relatively, you know, a consistent distribution, more or less. The black areas, by the way, are unmapped, not zero. Those are ones that they did not have the data for in their compilation. But you can see that when you get to the number of deltas over that region, certain locations are less prone to having rivers meet the sea and form deltas for various reasons, right? So some of those reasons may be because of the sediment load that's being carried, or because of the basin characteristics. If you know, if sea level is rising on average like it is now, and you're constantly filling in estuaries and so forth, and so the river is discharging its sediment, but it's, you know, sea level is rising and filling the basin faster than the sediment can fill the basin, you don't get a delta either, right? So you can see that distribution is not uniform across space, which is kind of cool. So the way that deltas form in these basins, and the reasoning for some of the differences in their style that we're going to talk about, has to do with the influences of the different processes and sort of the driving forces, their relative magnitudes, if you will, right? So if you can see in this diagram, this is sort of your idealized river entering crossing the coastline into a standing body of water situation. Rarely in nature does a channelized flow and coastline look quite like this, but you can see, so this is the receiving body of water, so this is be your ocean or your lake basin, and this is your river flowing in, and at the point at which the river crosses the shoreline, right, it starts to disperse. The flow disperses outwards, and the way in which it does that, and the deceleration and so forth, depends upon the inertial forces, how much strength that water has flowing downstream, and that's a function of the discharge, and it's a function of the slope and so forth, right? There's also buoyancy that can play a role. For fear of going into too much detail, the buoyancy of the water that's flowing in can be determined by its temperature. It can be determined by the salinity. Of course, rivers are fresh water, as well as the amount of suspended sediment. So the more suspended sediment, the denser the fluid is. right, that's entering the receiving basin, and the relative density difference between the river that's flowing in and the standing body of water determines the buoyancy of that, which determines a lot about the sediment transport processes. There's frictional processes as the sediment is deposited, forming bed forms and so forth. There's also basinal processes, right? So those are the waves, the tides, the longshore drift. So that's a wave-driven process where if the average incidence of waves is maybe coming from, at an angle to the shoreline, then you're going to get drift of flow and sediment. It manifests itself as a drift of sediment in one particular direction. So if you were to look at the coastline along the Gulf, you would see that we have a pretty predominant longshore drift from east to west here. And other kinds of currents as well. And so those things will all interact, and it's the relative magnitude of those that will form different types of deltas, okay? So we're going to take a little tour of some deltas and start to look at their morphologies and start to think about the differences in deltas. And as I say, there's there are thousands of deltas on Earth's surface, and so I'm just going to show you some of my favorites here and talk a little bit about their distinctions. So this is a really nice example of what one might call a relatively river-dominated delta, right? There are some estuaries indicating that maybe there's a tidal influence here, but you can see this is a really neat one because the river is running almost parallel to the coast for much of its path, but you can see at some point it avulsed or broke through its meander here on the outer bend to the coast, and now it's created a delta, whereas maybe somewhere further down the page here it would have before. But you can see in detail there is some wave influence. These mouth bars here that you see lined up indicate that there's wave or longshore current. Those would be wave produced mouth bars here that you see, that sort of these barriers, if you will, barrier islands, pretty much you would call those, I guess. But you can still see that it has very much a fan-like shape to it, indicating that the river is still able to push sediment well out into the receiving basin. So there is some river dominance to this delta. There is some wave apparent control on this delta as well. So this would have sort of a mixed type. This is the Niger River in West Africa, and you can see very beautiful, elongated, estuarine type sedimentation. The flow is distributed across multiple outlets here, right? And this is indicative of a tidally influenced delta, right? So there's a lot of suspended sediment, but there's a lot of these tie channels. There's a lot of interconnectivity of channels. This indicates that the river has significant tidal influence here. Okay. This is another gorgeous delta where you can see that it makes a delta shape, but just barely kind of makes it out to form a real proper, fan-like shape to it. And this would be because of wave and longshore currents. Once the sediment gets to the coastline, it gets sort of smeared along the coast, and that's indicative of a wave, longshore current kind of dominated coastline. Here's another gorgeous delta. These, have nice braided rivers that are feeding them, and you can see that there's both river influence. It's making its way out to sea, but it's also picking up. You can actually see it in this image. The waves are coming from the lower left corner over to the right, and you can see you're getting these barrier islands starting to form at the mouth of this river as the sediment is being transported along shore from left to right. I'm going to show you one of my favorite, our local deltas here. These are the Wax Lake and Atchafalaya deltas. If you're familiar with the Morgan City is off in this direction here. Homa is down here, or kind of over this direction. I took this from a plane, I guess right before the COVID days, probably the last time I flew out of here. So this is the Atchafalaya Delta here, which is a little bit more managed because they dredge for shipping, so that ships can make it up to Morgan City. But you can still sort of see it's very much a river-dominated delta. There's not a lot of tidal influence out here. The tidal range is less than a meter on average, usually less than about a foot. And so you can see these beautiful distributary networks, right? So the river enters the Atchafalaya Bay in this case, and the river starts to bifurcate. Okay, and that's a classical morphology of a river-dominated delta, where it's very much dominated by the bifurcation process as the flow sort of distributes itself across the landscape. Yeah, this is the Wax Lake Delta. So the Atchafalaya River main channel flows here. This was a dredged cut that was made for flood relief off of the Atchafalaya River, by the way. So this is not a natural channel here, but this is a natural delta in a sense, right? So, and here's what that looks like from sort of an oblique upstream to downstream view. So we're looking from, that view is from about here on the Wax Lake Delta, and you can look down at the delta front and you can see these beautiful islands that have formed as the sediment has accumulated in these interdistributary bays, it's called, and the elevation of those channels, they gradually trap more and more sediment and become exposed subaerially. The delta front itself actually stretches way out to, you know, a couple of kilometers out in front of here, so that we go out and do a lot of work on this delta. And if you were to take your boat out there, you could get 2 or 3 kilometers out and still be running aground and still be able to like jump out of the boat. There'd be channels, but there would be islands that are not actually exposed. They're maybe only, you know, a foot deep, which is a pretty neat depositional region. And so that sediment is being driven out of the channels up onto these islands that are not exposed, if that makes sense. And then eventually they get high enough, they start to get stabilized by vegetation, and then they can become permanent islands like these that you see here. Okay. And so this is pretty much dominated by river processes. This is a really cool delta here. This is the Elwha River Delta. This is bathymetry data, so these are surveys taken from a boat of the depth, and you can see the river is building out a delta. So in right before this, the beginning of this, I believe it was removed in 2008 or 2010. There was a dam that was removed on the Elwha River, and that dam had basically become filled up with sediment, more or less, and when they removed the dam, all of that sediment was able to be transported downriver and form this beautiful delta. And one of the things they track the bathymetry for this is behind all of these barriers, which are caused by the fact that there's wave and longshore currents in the area here. Oops, sorry. Is those become really important sort of wading grounds or resting grounds. I'm not exactly sure the terminology. I'm not a biologist. For salmon who are going to go and spawn up this river. It's a really critical salmon habitat. And so behind all these barriers, if you look at the right time of year in like early summer, you can see aerial imagery, and it's just chock full of salmon waiting to go upriver to spawn, which is pretty cool. And so this is a really neat delta that's kind of super dynamic on real times. Like this is, you know, on the order of a few years, the entire shape of this delta is just continually changing because it's being, it's receiving a ton of sediment from the river, but also a ton of reworking by waves and longshore currents. Which is pretty cool. And I can't show a delta stratigraphy lecture without, of course, showing a delta on Mars. This is one of my favorite. I think this is probably one of the prettiest deltas in the solar system, as far as I'm aware. So this is a really gorgeous delta from a location on Mars, taken from an orbital satellite imagery system. So you can see all of these channels fanning out Looks just like the Selenga Delta to me, but you can tell that it's not because it's got craters. So the processes here, just like with when we were talking about rivers and other things, are relatively similar and potentially kind of universal, and they are very scale independent, if you will, in that case, in that you can have a delta that might look very similar to this, that's this big in a little experiment, or you can have it on the order of hundreds or thousands of kilometers in scale, or on another planet, right? So that tells you that there's some fundamental physical processes that are occurring in these delta systems. And so one of the kind of root questions about deltas is why are they fan-shaped? What processes control the fact that sediment gets dispersed in this sort of fan-shaped manner? Especially with the river-dominated deltas, you get these really nice, not always symmetrical, but relatively symmetrical sort of half-circle patterns that form. And the reasoning for that is pretty apparent on this video. As the delta progresses here, it starts to channelize, right? So you can see how it started to form, a couple of different channels. And as it progresses further down, what those channels do is they both bifurcate, right? So as you get further and further down, the sediment starts to deposit as the slope decreases and you get into the standing body of water. So you get mouth bars that deposit and bifurcate, but you also get channels that switch. So you get both bifurcations and you can get avulsions that occur. And both of those things can work in conjunction to build out a delta deposit that has these sort of fan-shaped morphologies. Okay, so you can see as this delta continues to prograde, this is an experiment. These are walnut shells, like crushed walnut shell material that's being used to make this delta. You can see that as this delta progresses, the avulsion node tends to migrate down experiment, right? So it started where all the avulsions were occurring up here, and then it's over time moved down here, such that the delta has continued to kind of grow out, right? And this is kind of similar to what we talked about with avulsions in rivers, is either the channel can super elevate, or what occurs is, as you extend and extend and extend that deposit further and further out, kind of like we have done here at the Bird's Foot Delta on the Mississippi River, it eventually becomes such a low slope, such a low gradient, because it's gone so far out into the standing body of water, that it may become energetically more favorable for the river to go right next, to, if it avulses, or if you get a splay through a channel or through a levee, off to one side into one of the bays alongside the delta, it may become more favorable to just go that way because it's a steeper slope or a steeper gradient, right? The Mississippi River is a great example of a process like that, where it's trying to happen. The Mississippi River, left to its own devices, would have probably avulsed down the Atchafalaya River by now. Starting in the 1930s, the Atchafalaya River began to capture a significant portion of the Mississippi River's flow, and it's a much shorter distance between that location to the ocean, to the open water, than it is down to the mouth of the Mississippi River now. The only reason it didn't do that is because Congress mandated that only 30% of the flow can go down the Atchafalaya River, and made the Army Corps of Engineers responsible for maintaining that. So that's a relatively common and frequent process that ultimately causes these deltas to become this sort of fan shape, right? And you can see this on several of these deltas here, that there seems to be a sort of general location from which most of the larger channels kind of radiate out from, right? So you can see on this delta, here, here, here. I believe this is this is going to challenge me. I don't remember which delta this one is. This one is the Mackenzie, I believe, and this one is the Is this the Lena River, maybe? I'm probably mixing them up, especially the Siberian one here. But this is in Russia. Wait, I have to have this reversed. Sorry. Not getting my deltas right today. But these two are both Arctic deltas. Anyway, so you can see that there's a general sort of node from which the channels do currently or did in the past kind of emanate from, and those would be considered what we would call the avulsion nodes, right? And so you can see that you know, the delta itself can kind of form from the radiating avulsions and channels that originate more or less from that location, from that apex. And we would call that length the avulsion length scale, right? The distance, the sort of channel distance from that avulsion node down the river to the coast would be sort of that avulsion length scale, okay? And the drivers of these processes is really interesting. In many cases, this sort of delta nodal avulsion length scale has a very specific length scale associated with it. So if you look, for example, at the Nile River Delta in Egypt, right, this is the avulsion node of the Nile River here, and you can calculate what's called the backwater length of the river. And that is basically if you were to, if the river is sloping out towards the ocean, right, and it reaches a point where the bed slope continues to go down, but the water surface slope has to sort of gradually flatten out to meet with the ocean slope, which is zero, right? The water in the ocean or standing body of water will be flat. And so as that slope starts to diverge from the bed slope, you can measure the length scale over which the sort of backing up of that water, right? The flow is decelerating as that slope decreases, so you're backing up water, essentially, right? So we call that length over which that occurs the backwater length, right? And so the length at which the river basically feels the influence of that standing body of water in front of it, which corresponds to approximately where the ocean level kind of reaches the bed level, if you will, right? So where the bed level is at sea level, more or less, right? That's kind of the backwater length. And so you can calculate this based on the depth and the slope of the river channel, of the bed of the river, right? So if the slope in this case is 6.4 times 10 to the minus 5 here, right? That's the river slope for the Nile. And if the depth is something on the order of about 16.2 meters, then in this case the backwater length is depth divided by slope, right? So that's going to be, if the river is this deep and it's this, and the slope is this steep, right? It's this length that you're interested in, where this depth, the top of this, intercepts the bed back here, right? That's the depth at the mouth, by the way. And so you can calculate for the Nile River, the depth over the slope is 250 kilometers about, and the length of the avulsions is about 210 kilometers. So it sort of tells you that they're approximately equivalent. And you can plot this for some of the large river deltas and show that on average the avulsion length scale is approximately equivalent to the backwater length scale of these rivers. Okay, and that can give you a bit of information about how to predict where these avulsions are going to occur, or to potentially, if you're doing stratigraphy, think about if you know the depth and you can calculate the slope from an outcrop, you can predict where potentially if you don't have outcrop somewhere else, or you're going to try and go look for where the river mouth is, you can predict how far you might have to go back up section or up system in order to find the sort of avulsion nodes of these river deltas, if that makes sense. Okay. Now, that's for the nodal avulsions. There are other avulsions that can also occur on a delta. So you can see this is the Yellow River, the Huanghe River in northern China, and there are multiple locations at which avulsions will occur on this channel. So there are the nodal avulsions that occur further upriver, right? But then at the mouth, you can also get smaller scale, much more rapid avulsions, right? So this channel can fill up with sediment very quickly and rapidly avulse, rapidly avulse, rapidly avulse, and so forth on the order of, tens of years. Whereas this one, these nodal avulsions occur on the order of, multi-decadal to hundreds of year timescales, okay? And you can see that this avulsion node, as the delta has prograded, has also moved downstream. So it used to be further up here, right? And it has avulsed, continuously built out a ton of sediment. And as it does that, the backwater length remains approximately the same, but the distance, but that backwater location where that backwater length reaches moves basinward, right? So if the shoreline used to be here, then the backwater length reached to here, so that was the avulsion node. Now the shoreline is here, the backwater length reaches to here, if that makes sense to everybody. This is a really neat river system or delta system. It has an enormously high sediment load, especially of fine sediment. So it flows out of the Lus Plateau in northern China, and has just an incredible amount of very fine silt, and fine silt to fine sand. So the median grain size of this river is something like 60 microns or something around that range. And so it has a huge sediment load, and so it can avulse, super elevate, channels can migrate incredibly quickly. So it's a really neat system. We have a record of that here on the Mississippi River Delta. So you can see over the last 7,500 years or so, the river has avulsed primarily from this lobe here, or from a node somewhere in this neighborhood here. The backwater length, the backwater region, or the backwater node, if you will, would be somewhere right around up here. Okay, and you can see that's where the Atchafalaya River emanates from, right? The old river control structure is like right here, I believe. And so here's the Atchafalaya River coming down here. That's the most recent attempted avulsion that we have made not happen. But then you can see over varying time periods, the river has built out deltaic deposits and lobes in different locations as the river has avulsed and switched locations over time. And these actually manifest themselves in the current topography of Louisiana as the river levees, right? The high points along the margins of the river now become high topography surrounding bayous that are no longer receiving sediment, but still have a channel oftentimes in them. So you can see that much of the settlement of this part of Louisiana is centered along those high ridges, right? And so that you can kind of get a sense for where these old river deposits used to be based on those high ridges. Okay. And several researchers have gone out and cored and trenched and dated and done all of that work in order to reconstruct that history that I showed in the previous slide. So that's a little bit about river-dominated deltas and how their general process works in terms of why they form the shape that they do. But as we've mentioned here, and as well as in the lab, delta morphology can be quite more complex than that. And I've shown you this diagram. This is sort of a a bit of a heuristic or sort of generalized diagram about the relating the general morphology of a river delta or of a delta to the process that is the most dominant in its morphology. And we as a community go back and forth and have lots of discussions about what that actually means and how you can measure that. But suffice it to say that generally speaking, the rivers that have, you know, mouth bars or sorry, barrier islands like this, or have these sort of cuspate shorelines like this. Apologize again, that spelling error keeps rearing its head on this diagram. These cuspate shorelines are generally speaking considered to be more wave dominated, as the waves either rework the sediment at the mouth of the river and create those ridges, right? Or as the longshore currents driven by waves that are not directly impacting, you know, at a, you know, perpendicular to the shoreline. If they're coming in at an angle, then they can cause sediment to drift down down the shoreline in one direction and smear out that sediment. So these would be indicative of wave-dominated systems. In river-dominated systems like we live in here, you get these very elongate, you know, lobes that sort of deposit, you know, as the river is able to prograde further and further out before it avulses, and so forth. So you get long channels. You don't get a ton of interconnectivity between the channels per se. Whereas as you get more into the tidal-dominated systems, you get the elongated bars, but you get an interconnectivity of tidal channels, right? So the channels that make it to the coastline are not necessarily always receiving fluvial sediment, right? But they may be receiving sort of ebb and flood tide sediment and flow and sediment that routes through them. And so you get these islands that are interconnected, and this channel might be connected to that one, might be connected to that one, and so on. If that makes, if that's clear. And so you get these tidal estuaries develop in these systems. So here's a delta. Here's a classification of those with some actual delta imagery, so that you can have some maybe specific examples. Now you can probably go find, based on these names, you can go find these images and see a little bit clearer pictures of each of these. But you know, this, like the Niger River Delta, which I showed you before, it has a very nice, clean, linear coastline, which indicates that there's wave processes that are taking place to sort of smooth out that coastline. But at the same time, you also see those long, interconnected estuaries, which also indicate a large tidal influence as well. Whereas you get to the Nile, which has a much more, you know, it's starting to develop a more radial, right, or fan-like pattern to the channels, so they're not as interconnected like they are on the Niger Delta, but they still have that smeared out kind of coastline as well. So it tells you that there's wave-dominated, but also partly fluvial-dominated as well, right? Similar to the Ebro, which is extending much further out into the basin, so it's getting more elongated into the basin, right? So more fluvially dominated. Then there's the Mississippi, which is quite fluvial dominated, although with the barrier islands and things, we do get some longshore currents, but not a ton relative to the sediment transport of the river itself. And then you get into the Fly River again. These are those long estuarine systems. Same with the Ganges, Brahmaputra, these nice long estuaries. They're interconnected. They're not necessarily distributary like the river dominated. It's not all like originating from a single lobe and distributing outwards. Some of them are more complicated than that, especially in the Ganges and so forth. Okay. And just like anything, it can get even more complicated than that. It may depend not just on the the form doesn't depend just on the waves, tides, or rivers, but also can depend on the sediment load and the sediment caliber. So you get different morphologies of these kinds of rivers, slight variations on the theme, if you will, depending on whether you're in a gravel or a sand or a mud-dominated system. Okay, so some of those distinctions are given here. The drawings for these are not that clear in the figure, but if you want to understand those in a little more detail, you can definitely go look up all of these rivers on Google Earth or something like that. Okay. So again, we've kind of talked about these in a lot of detail, but some examples of some river-dominated deltas that I mentioned. Here's the Wax Lake and the Atchafalaya. Again, you can see that only the sort of levees are above sea level. There's interdistributary bays here that get filled in with mud, and they produce the whole system protrudes quite far out into the standing body of water. The Wax Lake Delta, for example, you can see sort of just vaguely in this image, there's a bifurcation that's occurring that you can just kind of see in the sediment pattern here. This is probably about where the delta front is here. So you can see it goes quite a good ways out past the sort of subaerially exposed shoreline. Okay. And that's because you're sheltered in the Atchafalaya Bay from waves to a good extent, although you do get some wave action here. But and we're in a microtidal system, so the tides are relatively unimportant here as well. Okay. Although the tides also do have some influence, they generally do not direct flow up channel. Okay. On wave-dominated deltas, the sediment, again, is being constantly reworked, so it gets delivered by the river, moved around by waves as they're approaching, or smeared around by longshore currents as the wave approaches from a perpendicular direction. And so you see these features associated with sort of the smearing or smoothing out of the shoreline. Okay. There's some great examples of these where you get these beautiful beach ridge complexes where you get different generations of shoreline development that smears out and has a big influence on the sediment, the depositional patterns that you might expect to see. Okay, here's a great example of that from Mexico, those beach ridges, right? And again, in tide-dominated deltas, the delta shape is essentially shaped by the continuous redirection of flow, if you will. So every 6 to 12 hours, depending on the time of month, the currents will potentially either slow down or stop if it's a relatively low tidal range, but they can also reverse, right? So you get sediment transport that goes down river, and then that sediment transport can then go upriver again during rising tides. Okay, and so what that results in is basically a sort of two-directional channel, almost, if you will, that results in these tidal islands and estuaries that can kind of be interconnected and much more complex in its morphologies than in many fluvial-dominated systems. You often also see those funnel-shaped mouths, right? So this is a great illustration of that. Right, you can see how you sort of get these interconnected channels, but right at the mouth it sort of opens up quite a bit, and oftentimes there's these elongate islands and bars inside there. You can see that there, right? You can see it here, right, and so on. Here's another great river example of that, the Fly River. Here's another beautiful sort of funnel-shaped mouth. and you can see all of the interconnected estuary systems here. Okay. One kind of cool thing to think about is, as we know, the world's coastal systems, climate, sea level, etc. are changing. And this is a really cool paper that was just published last year, thinking about what those changes mean in terms of the dominance of different deltas across the world's coasts. And one really interesting trend that you notice is that in general, because of rising sea level in particular, and because of potential things like storm intensification and so on, is that if you compare the relative sediment transporting power, or the ability of the different currents, tides, and waves to move sediment, you see that rivers will, on average, start to become, or at least many rivers will become, more wave or tide dominated and less river dominated, right? That over time, because of rising sea level in particular, and some other factors, that the river dominance of deltas will decrease, which is kind of a cool thing to think about. And in particular, for some of the really big rivers of the world, those differences might be quite large. Some will change towards the river dominated. So the Lena River, for example, which is an Arctic river in Siberia, might become more river dominated. This may, have to do with changes in storms in the Arctic Ocean or what have you. But most of these large rivers, like the Mekong, the Mississippi, the Copper, the Nile, the Ebro, and so forth, are going to be moved towards the wave or tide dominance, which is kind of a cool thing to think about. So we can talk now a little bit about the architecture of these sediments that are deposited in these systems, to kind of get a sense for what to expect to see if you see one of these deltas in outcrop. And the first thing that I'll note is, at the largest scale, we talked about this in the lab, is that the sort of big picture average delta deposit is going to look something like this in cross section. So we've now sliced the delta down the middle from, say, the Volscian node to the coast, down straight down one of those river channels, for example. And you'll see a geometry that might look like this. And the terminology that we use for that is, there's these flat fluvial dominated sediments on the top of the delta deposit. Those we would refer to as the top set, right? So that's the rivers, moving around on the top of the delta depositing sediment. There might be lake sediments up there, or interdistributary bay sediments, and so forth. And those prograde out on top of these foreset deposits. So once the river reaches the sea, it starts to drop out that sediment, and that sediment builds out a foreset, right? It builds out a slope out in front of the delta, right? And in most systems, that generally is deeper than the river channel itself, although not entirely true. And so those foresets will be, some thickness larger than the top set oftentimes, okay? And then finally, some of the suspended sediment might make it further out. You saw like the images of the Wax Lake and Atchafalaya River, where there were the big sediment plumes that made it out really far beyond the sort of coarse material transport that would settle out to these foresets, and those would form sort of more deposits that would extend more out basinward, called bottom sets. Okay. And these become more, marine type deposits at that point. Okay. And so what that progression might look like is, oftentimes you think about a prograding river delta. So that's prograding, meaning it's moving outward into the basin. It's building, started here, and it's building outward. So progradation means the deposit is moving towards the basin, right? And you might see in, say, a stratigraphic section then, you would start out with your bottom set deposits, right, which are finely fine-grained. Maybe they're slightly inclined out towards the basin sediments. And then you would have your foreset of coarser material laid down on top of that. Those would be dipping at some angle, depending on the type of sediment, anywhere from a couple of degrees to, you know, a couple of tens of degrees up to angle of repose if it's coarse gravel, for example. And then finally, on top of that, you would end up with your top set deposits, maybe resembling fluvial deposits, right? River deposits, gravel and sand, channelized, etc. Okay. And you can see this in various scales, anywhere from, this is an experiment tank, you know, a few tens of centimeters, where again you can see the top sets deposited on top here. Then you see the foresets that are sloping down towards the basin, and then the bottom sets, which are sort of this suspension settle out here at the bottom. And this could be at any range of scales, all the way from this experiment up to, say, seismic scale. These are delta cliniforms in a dip section off of Greenland. Apologize, I don't have a scale bar on here, but I would say probably, let's see here, I would estimate this to maybe be 2 kilometers or more in thickness. I have a scale bar for that somewhere, a scale version of this image, but this, you know, it can be on the order of kilometers deep, right? And go all the way to the extremes, and say the Mississippi River Delta, there are places, you know, where the foresets are, you know, 8 kilometers or 6 kilometers high, all the way up to, that may not be quite true. The foresets maybe not that tall. But certainly in the Ganges Brahmaputra River Delta, they get in the order of 5 to 6 kilometers, and the sediment thickness can be huge because it's subsiding as well. Okay. And so what that stratigraphic section might look like in detail for a prograding river delta is a typical sequence that coursens upwards, right? So you start out with your fine muds, and as the delta is prograding towards you, you end up getting coarser and coarser and coarser as the, you know, mouth bars start to move in, and the more sand material or gravel material, depending on the system, becomes more apparent or more abundant in your system, right? And then at a certain point, typically what happens is an avulsion or an abandonment causes the system to change, usually very quickly, right? So you've gone from being, you know, your bay or your offshore conditions, and then say a crevasse splay or an avulsion comes in here and starts the river prograding towards your location where you've measured the section, right? So now it's getting coarser, and then all of a sudden the river decided to avulse and go someplace else. Then you end up creating open bay deposits again, and usually this is a very abrupt transition from a coarsening upward sequence right away into a fine-grained sequence again. And that system might repeat itself multiple times as the river avulses, returns on, you know, hundreds or thousands or more year timescales. Okay. So again, this could look like any number of coarsening upward sequences depending on the grain size. So here's an example of the pro-delta. So these would be the delta front deposits, or the delta toe deposits, I mean, up to the delta front, to the delta top as you coarsen again, and then this would be the delta plane as the deposit progrades even further. Again, similar kind of thing. It could be at any range of scales for any range of grain sizes. So that's something to look out for in a deposit like this, on the order of, you know, depending on the system, meters to tens to hundreds to thousands of meter scales, you get these consistent coarsening upward sequences. There's a great example of this in what would have been our field trip in Arkansas, that I would have loved to have taken you to. But there are plenty of examples of this in the stratigraphy here. Unfortunately, we can't see it in person, but you can certainly see seismic and core data that does exist, much of it public, showing this kind of coarsening upward sequence from very fine-grained muds to coarser grained sediments. So that wraps it up for our discussion of deltas, and in the next lecture I'm going to talk a little bit more generally about coasts and beach type processes. Okay.